So we've talked about how to mechanically athermalize a doublet in this case, and we're going to move on to an example of how to calculate for L4. So using a commercially off-the-shelf achromatic doublet, we can actually calculate the thermo-optic coefficient. And the thermo-optic coefficient of a specific lens element is actually equal to the thermal expansion coefficient of that lens material minus 1 over the index of refraction minus 1 times the change in index of refraction with temperature. And it has units of 1 over degrees Celsius. Now, for a doublet, we can calculate the individual thermo-optic coefficients of each lens element using this equation, and then we can bring them together in order to determine the thermo-optic coefficient of the doublet itself. So in this example, lens element 1 is NBAF10, and lens element 2 is NSF10. And these have well-characterized parameters for each of these variables in this equation. So the thermal expansion coefficient of lens element 1 is equal to 6.18 times 10 to the negative 6. The reference index of refraction is 1.67003. And the change in index of refraction of lens element 1 with dt. In this case, we're going to be going from 25 degrees C to 50 degrees C is equal to 3.849 times 10 to the negative 6. For lens element 2, the thermal expansion coefficient is equal to 9.40 times 10 to the negative 6. The index of refraction is equal to 1.72828. And the change in index of refraction with temperature is equal to, between 25 degrees C and 50 degrees C, is equal to negative 7.012 times 10 to the negative 10. So now we can determine the thermo-optic coefficient of lens element 1, and that's equal to 6.18 times 10 to the negative 6 minus 1 over 1.67003 minus 1 times 3.849 times 10 to the negative 6. And the thermo-optic coefficient of lens element 2 is equal to 9.40 times 10 to the negative 6 minus 1 divided by 1.72828 minus 1 times negative 7.012 times 10 to the negative 10. Now this side of the equation simplifies to 5.745 times 10 to the negative 6. So you have negative 6 here, similar magnitudes. On this side, we have negative 6 and negative 10. This term is so small that it essentially can be thought of as 0 because it has such a tiny contribution to the thermo-optic coefficient compared to the thermal expansion coefficient. And so we have something kind of interesting here where the dn dt of lens element 2 is so small that the thermal expansion coefficient dominates, whereas for lens element 1, the thermal expansion coefficient and the dNdt term kind of cancel each other out. And so the thermo-optic coefficient for lens element 1 is quite small at 0.435 times 10 to the negative 6, 1 over degrees Celsius. And the thermo-optic coefficient of lens element 2 is equal to 9.40 times 10 to the negative 6. So even though the dNdt of this lens material is tiny, you do have a significant thermo-optic coefficient. And even though the dNdt of lens element 1 is significant, it cancels out the positive thermal expansion of the lens material. So now I'd like to actually visualize what's going on here. So on this axis, if we plot the change in focal length over the original focal length, you can think of this kind of like strain, also delta L over L naught. And this would be 0, this would be 200, this would be 400, 600, and 800, all times 10 to the negative 6. And this would be negative 200, negative 400, negative 600, negative 800. And if this is temperature on this axis, and this is 25 degrees Celsius, and this is 50 degrees Celsius, we can plot these thermo-optic coefficients by determining the slope of a line on this graph. So the displacement, or the focal length change, if you will, of lens element 2 will be positive, and the slope right here is beta 2. So at 25 degrees C, that's our reference temperature, that's 0. At 50 degrees Celsius, you have close to a 200 times 10 to the negative 6 change. Because remember, this is 9.4 times 10 to the negative 6 per degrees Celsius. So a 25 degree C change will result in a focal shift. Now beta 1, this is very, very small, and it actually hugs the 0 line. And so this would be lens element 2, and this would be lens element 1. And there is a slope there. It is quite small, but that slope is beta 1. And so both of these thermo-optic coefficients will come together to create the thermo-optic coefficient of the doublet. And the equation to combine these two is quite simple. It's the thermo-optic coefficient of the doublet is equal to the focal length of the doublet divided by the focal length of element 1 times the thermo-optic coefficient of element 1 plus the focal length of the doublet divided by the focal length of element 2 times the thermo-optic coefficient of lens element 2. Now this equation is actually quite similar. It's of a very similar form, not exactly, but a very similar form to the way we expanded the thermal expansion coefficients and combined the thermal expansion coefficient and the length of the two housing materials to athermalize the system. So for this particular lens, or this particular doublet we're looking at, the focal length of the doublet is equal to 43.5606 millimeters. The focal length of lens element 1 is equal to 21.4133 millimeters. And the focal length of element 2 is equal to negative 33.8093 millimeters. We can use those in this equation and what we calculated previously to determine the thermo-optic coefficient of the doublet. So bringing all of it together, the thermo-optic coefficient of the doublet is equal to 43.5606 divided by 21.4133 times 0.435 times 10 to the negative 6, which is that, plus 43.5606 divided by negative 33.8093 times 9.40 times 10 to the negative 6. This term goes to 2.03, and this term goes to 1.29. Multiplying out, the thermo-optic coefficient is equal to 0.885 times 10 to the negative 6 minus 12.11 times 10 to the minus 6. And therefore, the thermo-optic coefficient of the doublet is equal to negative 11.22 times 10 to the minus 6, 1 over degrees Celsius. This is very interesting because this is negative. In fact, the thermo-optic coefficient of the doublet, it's not in between the thermo-optic coefficients of lens element 1 and 2. It is negative. D. And the reason is the lens element that has the highest contribution to the thermal focal shift has a negative focal length. And that negative focal length results in the domination of the thermo-optic shift, thermo-optic coefficient of the doublet itself. So we don't really have any real materials, normally, that have a negative thermal expansion coefficient, but our ALLVAR alloy material does. So this is a thermal expansion of ALLVAR alloy 30, where the slope is alpha ALLVAR, and this is the thermal expansion coefficient of aluminum. And so we can tune any thermo-optic coefficient that falls in between this line and this line. Anywhere in between, we can use a series of aluminum and ALLVAR alloy 30 to athermalize an air gap. And in this case, we can use it to athermalize the thermo-optic coefficient of this doublet. So we know that the length of the housing is going to be equal to the focal length of the doublet. And in this case, it's equal to 43.5606 millimeters. So that's already a known number. We have the thermo-optic coefficient, and we can then use that in the equation that we developed for a particular housing element, in this case element 4, and setting it equal to the thermo-optic coefficient of the doublet minus the thermal expansion coefficient of another housing material divided by the thermal expansion coefficient of element 4 minus the thermal expansion coefficient of another housing material, all times the length of the housing, which again is equal to the focal length of the doublet. Now we can set alpha 4 to be equal to the thermal expansion coefficient of ALLVAR, and we can set the thermal expansion coefficient of aluminum equal to alpha 3, and that will equal 24.6 times 10 to the negative 6. In this case, it's equal to negative 30 times 10 to the negative 6. Again, this is 1 over degrees Celsius, 1 over degrees Celsius. Now we can bring it all together. So the length, instead of element 4, the length of the ALLVAR component is equal to negative 11.22 times 10 to the negative 6 minus the thermal expansion coefficient of aluminum, 24.6 times 10 to the negative 6, divided by the thermal expansion coefficient of ALLVAR at negative 30 times 10 to the negative 6, minus thermal expansion coefficient of aluminum at 24.6 times 10 to the negative 6, all times that focal length, which is 43.5606 millimeters. And the units here will cancel. So the length of the ALLVAR to athermalize the doublet that we've been talking about is going to be equal to 28.578 millimeters. And delta T, in this case, is between 25 degrees C and 50 degrees Celsius. But the beauty of this equation is that it doesn't need to be confined to only a doublet. Any thermo-optic coefficient for any complex system can be plugged in to determine the length of ALLVAR needed relative to aluminum to athermalize the system. And so now you can take your known, tried and true aluminum SM1 tubes, and you can prototype with an ALLVAR tube and athermalize air gaps, athermalize doublets, and athermalize more complex lens systems.